Okay, so I guess, mostly wrapped up talking about Laplace last time. Today, we're going to start talking about numerical solutions to 1D non-steady state problems. So if you remember back, previously when we've done numerical solutions, it's been in either just space, right? We just have some discretization as a function of x and or y. And then we also did numerical solutions that were transient, but those are 0D, so say lump capacitance type problems. Okay, so now we're combining the two concepts, the two approaches that we've done before, bringing those together to have a technique you can use to solve problems where you have conduction, you have energy state changing as a function of time, but you're doing both of those things together. And there's really not that much new here, except that what we're doing is a little bit more complicated and just slightly different dimensions. Okay. So let's get started here with kind of going over the approach for this. So there's, I'd say, like basically 3 steps here. The first step is step 1. We're going to start by distributing our nodes spatially throughout the computational domain. Right, so we're going to start by discretizing. We're going to take as an example this fin problem that we have here. We're going to look at how this thing changes as a function of time. So let's say there's some initial condition. You're at t infinity. This fin is just sort of sitting there doing nothing, and then at time equals 0, we activate it in some way. We're starting to put heat through the base of the fin, or we're changing the ambient condition or something like that. Right, so we'll use this example to kind of go through the approach here, but we start by distributing nodes in space. Then we carry out an energy balance on each node. All right, so if you think through that a little bit, we're going to end up with internal energy is changing as a function of time, right? And that's true at every single node. So we end up with a bunch of state equations, one for each node. Right here we'd say I have dti dt, right, where I is the node in space. And so I've got a bunch of these different state equations that depend on both time and a vector of temperatures. So this, let's write it out. This t bar here, t bar is a vector of temperatures. Don't get confused. That's not average temperature. It's a vector of temperatures. Okay, so we have a vector of temperatures, one value for each node. Okay. So we compute the state equations for each node, and then step 3 here, we then integrate the state equations moving forward through time. And so once you set up the problem and you've figured out how to calculate those the dt for each node, then it's just choosing the right technique. So let's start by doing kind of the spatial energy balance. What we're going to do first is we're going to go through and compute energy balances for each node, right? And we'll do that once for each of the boundary conditions and once for the nodes in the middle, because they're all the same. So we'll do that first, and then we'll see how to move that forward in time. Okay, so first thing we're going to do is distribute nodes spatially. So you can see here, right, I've got a node at the boundary. I have some nodes in the middle, and then I have another node at the right-hand boundary. So we have nodes on the boundary. Again, that's really important. It makes it a lot easier to enforce boundary conditions. I think I said it before, but it's actually not critical. Like you can still solve the problem without doing that. It just makes it harder. So we have this spatial distribution. And then in order to compute the position xi of each node, we would say that that's the same thing we did before. It's I minus 1 over n minus 1. So we have n spatial nodes for I equals 1 to n. Okay, and then the distance between nodes is going to be delta x is equal to, let's see, what is this? This length over here is L. So this is just L over n minus 1. So I'm missing an L here, aren't I? Yeah. Sorry, this should be I minus 1 times L here. 3. Yeah. Okay, so we have discretized in space, just as simple as what we've always done for the spatial distribution. Next thing is step 2, going to carry out an energy balance on each node. So let's do this first for the internal node, node I. So I've already drawn this out, but let's talk through it. So we have from node I-1 to I, right, we have heat transfer due to conduction. Now, this is a 1D problem, so we better make sure we have conduction happening, right? We have from the right-hand side, also conduction. We have convection coming in. And remember this convection, I drew it from the bottom, but this is convection for the entire exposed perimeter of the fin times the width of the node, right? So it's dx times perimeter. That's the area that's exposed for convection. If we had radiation or anything else happening, that would also be drawn in that way. Okay, and then the new thing here is we've got du dt, right? This node has some internal energy change. It's a little hard to see. The internal energy change is a function of time, du dt. Right, so that's really the only difference compared to the previous approach for 1D, but then it makes us have to get to a set of state equations before we could sort of solve everything at once. Okay, so let's go through and do our energy balance here. So we have Q dot LHS plus Q dot RHS plus Q dot convection is equal to du dt, right? So I have everything going in. All my arrows are drawn going in. I'm going to write my temperatures in accordance to that. And then we have stored energy, which has a negative term. So it becomes everything in is equal to what's stored. Okay, so writing this out, let's write out rate equations for each of these. So Q dot left-hand side, we have conductivity times the cross-sectional area over delta X times Ti minus 1 minus Ti. That's from the left-hand side. And we said Ti minus 1 minus Ti because the arrow is going from I minus 1 to I. Okay, and then from the right-hand side, we have something similar, KAC over delta X, Ti plus 1 minus Ti. And then due to convection coming in, right, we have, let's see, what do we call it, just H bar? So H bar times the area, so that's the perimeter, times delta X. Right? That's the surface area that's available for convection, times T infinity minus Ti. All that has to equal du dt. So du dt now, what's my internal energy component of this? Right? We have rho times density, rho times C times the volume. So what's the volume of my node? The volume of the node is the cross-sectional area times the thickness of the node, right? Not of the fin or anything. So that is perimeter, cross-sectional area times the thickness delta X. Okay, and then times the temperature, the time evaluated at I, node I. Right? So there's our energy balance for this particular node. If we went through and wanted to solve this, right, the goal is to get to some function or some state equation, right? So we want to actually solve for this dt and then use whatever MATLAB or whatever to compute this value, and then use this value for us to step through time. So in order to do that, we just sort of rearrange things. It ends up being dt dti is equal to, we'll introduce our thermal diffusivity alpha to simplify things a little. So it becomes alpha over delta X squared, Ti minus 1 plus Ti plus 1 minus 2 Ti. So we're bringing both of those in, plus H bar perimeter over AC rho times C times T infinity minus Ti. Right? And this is, what's this? What just happened? Oh, there we go. Okay. So that is for all nodes I equals 2 to n minus 1. Right. So now we have a state equation dt dt for node I in terms of what? In terms of all the temperatures at this particular moment in time, right? And this node I only sees the temperatures to the left and right of it. Right? This is the numerical assumption is that you can kind of localize the problem in this way. So we have this algebraic equation that gives us a state of a rate of change of temperature with respect to time at a given node, right? So we've done this now for node I. Any questions on this so far? Right? It's pretty similar to what you've done before, right? So let's do this for the other two parts here. We'll do it kind of quickly since it's basically the same thing. So again, on node 1, this is a node that's attached to the base. We have our energy balance is Q dot plus Q dot right-hand side plus, let's see, what do we make our assumption? Oh, Q dot here is our left hand, right? This is from the left-hand side. Plus Q dot convection is equal to du dt. Okay, so we go through and do this. Now we don't know what this Q dot is yet, right? We don't know what that Q dot is. I think in this, let me see what we said in this particular problem. We do know it, right? So this problem is specifying Q dot going into the base at time equals greater than or equal to 0. So that's actually what we're doing when we're activating this fin. We're forcing a particular heat transfer to go in. Okay. So we know Q dot, it's a constant. Okay, so then if we write out the energy balance, we end up with this constant Q dot from the left plus KAC over delta X times T2 minus T1. Right, that's from the right-hand side. And then due to convection, we have H bar perimeter times delta X over 2, right? Because our exposed area is only half of the normal node width. Okay, delta X over 2, and then let's see, where did I go here? Times T infinity minus T1. And that has to equal du dt, which is rho C times the volume, which is AC delta X over 2 again. Don't forget that delta X over 2 times dt 1 dt, or dt evaluated at 1. Okay, so that's our second equation here. So now we have n minus 1 equations. We just have to do this again for the last part. I'll spare writing out the full dt state equation. So then for this node, we end up with from the left-hand side, so Q dot LHS. It's adiabatic from the right-hand side, so there's nothing there. And then we just have convection. Convection is equal to du dt. So this becomes K AC T n minus 1 minus Tn, that's from the left-hand side, plus H bar perimeter delta X over 2, T infinity minus Tn. And that has to equal rho C AC delta X over 2 times dt dt evaluated at n for node n. All right, so we could easily solve both of those two equations for our rate and go from there. Yeah. Let's see. Oh, yep, sorry, I missed that. Good catch. Delta X here. Delta X here. Yeah. Got it. Okay.